We usually spend our time talking to AI generating text, maybe some video or,
Yeah.
the occasional surrealist image.
Yeah.
But if you look at the NVIDIA updates from January 11th through the 18th, the focus just is shifted completely.
It really did. It feels like this was the week we stopped talking so much about generative AI and started talking about physical AI.
That's the distinction.
Yeah.
Industrializing intelligence.
That's it. We're not just looking at models that live on a server anymore. The headline news, of course, is that massive collaboration with Eli Lilly.
$1 billion. That is not a pilot program.
Yeah.
That is a fundamental restructuring of how science is done.
It is. Announced on January 12th, it's a joint investment to build a physical AI lab, a co-innovation lab right in the Bay Area.
And to really get why that matters, why Jensen Huang is calling it a blueprint, we have to look at everything else they released this week.
Exactly. Because they rolled out the agents that can talk, the robots that can act, and even the security patches to keep the whole thing from falling over.
So let's start with the agents. On the 15th, NVIDIA's Applied Deep Learning Research Team, ADLR, they published a paper on something called PersonaPlex.
Right. And this seems to be attacking a very specific bottleneck in conversational AI.
The latency, the lag.
The lag, yeah. Historically, if you wanted a custom voice agent, one with a specific persona or an accent, you had to chain models together.
ASR to text, then the LLM thinks, then TTS for the voice.
And that cascade creates that awkward pause. It feels stiff. You can't interrupt it.
And you lose those little back channel sounds.
The things that signal you're actually listening. PersonaPlex is a full duplex model, so it's listening and generating audio at the same time.
Okay, so you can just prompt it with text, be a helpful medical assistant or something.
Or be a chaotic neutral gamer, and it just adopts that persona instantly, and it can handle interruptions. It makes the whole interaction feel natural.
Which is critical if you're moving these things into, say, a drive-through. But maybe more. Revolutionary or maybe alarming is what they're doing with the command line.
Oh, yeah. The research on training command line interface agents, that also dropped on the 15th. They're using a model, Nematron Nano 9B V2, for this.
And giving an agent access to the CLI, that's a totally different beast than just letting it browse the web.
It's direct system control.
Yeah.
Which is why the how is so interesting. They used reinforcement learning with verifiable rewards, RLVR. So they generate all this synthetic data to teach the agent how to do complex tasks in the terminal without a human coding it.
But how do you stop it from, deleting the entire system?
Well, that's the safety-first architecture. They had to build that in. It's strict execution isolation.
Sandboxing it.
Yeah, exactly. The agent runs in a sub-process where shell false. So it can't just execute arbitrary commands. It needs a specific handshake or even a human confirmation step.
They're trying to solve the computer use problem without creating a security hole.
A giant security hole. And speaking of security nightmares, this whole industrialization of AI, it creates new vulnerabilities, right?
Of course, if you have agents running system commands or designing drugs, the developer tools themselves suddenly become these high-value targets.
And we saw a perfect example of that. On January 14th, NVIDIA's product security team disclosed a high-severity vulnerability.
And Insight Graphics for Linux.
Yeah, that's the profiling tool developers use to optimize their code.
CVE 2025-33206.
And it allows for command injection and privilege escalation. I mean, if you're a bad actor, compromising a developer's profiling tool is a golden opportunity.
There's a backdoor. You could get access to proprietary source code,
Yep.
or, in this biopharma context, confidential molecule designs.
It just highlights that AI safety isn't just about model alignment. It's about hardening the entire supply chain. You can't build a billion-dollar biolab if your dev tools have open doors.
And all of that security, it sits on top of the infrastructure. We saw some really important updates in the, let's call it the plumbing this week.
Right, particularly that driver update on January 13th for the Blackwell platform.
This is the Linux driver 580.126.09. It introduced coherent driver-based memory management, CDMM.
Right, for the GB200 systems. And the GB200, that's the super chip that combines the Grace CPU and the Blackwell GPU.
The scale of memory on those things is just so vast that having the normal operating system kernel manage it becomes a bottleneck.
So they're bypassing the OS?
In a way, CDM moves that memory management right into the NVIDIA driver. It allows for coherent memory access between the CPU and GPU at a scale that the standard Linux kernel just isn't built for yet.
It's a pretty clear signal that the hardware is outpacing the legacy software stack.
They're rewriting the OS rules to fit the hardware. Which, speaking of software, let's talk about the TensorRT LLM update from the 15th.
Version 1.2.0, release candidate 8. The big thing here for me was the broadened model support. They added DeepSeek v3.2 and GraniteMo.
And DeepSeek has been getting a lot of attention. It's a really high-performance open model coming out of China.
It is, and NVIDIA's strategy here seems pretty clear. Be neutral. Be Switzerland. They want TensorTLMM to be the go-to inference engine for enterprise.
It doesn't matter if you're running Llama or a Google model or DeepSeek.
They just want to make sure their GPUs are the most efficient place to run it.
And efficiency really is the name of the game. I also saw a new guide on optimizing CUDA tile matrix multiplication.
Okay, that's getting pretty deep in the weeds, but it matters.
It does.
Matrix math is the absolute bedrock of all these models. So helping developers optimize that at the kernel level, literally how data moves across the chip's tiles, that squeezes out an extra 5, maybe 10% performance.
And when you're training on thousands of GPUs, that translates to millions of dollars.
Exactly. Millions in power savings.
Let's pivot a little to the visual side, because usually when we talk DLSS, we're talking about frame rates in, I don't know, Cyberpunk.
Right, in gaming.
But with the update to DLSS 4.5 on January 14th, I feel like there's a much broader application here.
Oh, for sure. Yes, it adds dynamic multi-frame generation, which is great for gamers. But think about what that tech actually does. It's using AI to predict and generate visual data in real time.
Which is exactly what you need for simulation.
Precisely. If you're training a robot in a digital twin, using Isaac Sim, for instance, you need that simulation to run as fast and as realistically as possible.
So the same tech that makes a video game look smooth.
Lets a robot run millions of training cycles in a virtual warehouse before it ever touches a real box.
And that bridge, from the virtual simulation to physical reality, that's where we see the biggest return on investment this week.
This brings us to the Multiply Labs story.
Yes, this is a perfect example of physical AI in action. Multiply Labs is using Isaac Sim and GR00T.
That's NVIDIA's foundation model for humanoid robots.
Right, and they're using it to automate cell therapy manufacturing.
Which is notoriously expensive because it's so personalized. You're modifying a patient's own cells.
It's a manual, almost artisanal process. It can cost over $100,000 per dose.
By using these simulation tools to train robots to handle the fluid transfers, the instrument manipulation, Multiply Labs dropped that cost by 70%.
70, so down to what, around $25,000?
Around $25,000. And that is the difference between a niche treatment for the wealthy and a potential standard of care.
It completely validates the tech. The simulation works, the robots work.
And that sets the stage for the main event, the industrialization of biology.
The Eli Lilly partnership.
Yeah.
We mentioned the billion-dollar investment, but what's the actual tech here? It's not just about faster computers. It's this idea of a lab in the loop.
Right. Lab in the loop is this concept of closing the gap between the dry lab, the computational side, and the wet lab, the actual biology.
And right now, that loop is incredibly slow. You design a molecule, you wait weeks for it to be synthesized, you test it, you get the data back.
And this new lab is designed to automate that entire cycle. They are co-locating NVIDIA engineers with Lilly scientists, and they're using the BioNeMo platform and what they're calling the Vera Rubin architecture to drive it.
Okay, I want to clarify Vera Rubin here. In this context, that's a specialized compute architecture just for these workflows.
Yes. Jensen called it the engine for this new industrial revolution in biology. It's optimized for this kind of high-throughput analysis. But the key isn't just the chip, it's the models. On January 12th, NVIDIA released major updates to BioNeMo.
This includes the RNAPro model and something called ReaSyn v2.
Right. RNAPro predicts RNA structures, which is vital for things like vaccine development. But ReaSyn v2, that one addresses what they call the last mile problem in drug discovery.
Because you can design a molecule that binds perfectly to a target,
Right.
but if you can't actually make it in a test tube,
It's useless. It's a fantasy. ReaSyn v2 predicts the chemical synthesis pathways. It tells the chemist or the robot, here's the recipe to actually build this molecule physically and economically.
it stops the AI from hallucinating impossible drugs.
And to execute those recipes, you need instruments. That's where the Thermo Fisher partnership comes in, also announced on the 12th.
Thermo Fisher, they're the giant in scientific instruments. Cryo-electron microscopes, mass spectrometers.
And they are integrating NVIDIA's edge compute, DGX Spark, directly into those instruments. So now a cryo-EM microscope can process terabytes of data in real time right there.
At the sensor level.
At the sensor level, it can identify a protein structure while the experiment is still running, instead of you waiting for days of post-processing.
So you have the AI designing the recipe with BioNeMo, the robot executing the recipe, like with Multiply Labs.
And the microscope analyzing the result in real time with Thermo Fisher.
And all of that data feeds right back into the model to make the next design even better.
That is the billion-dollar vision. You're turning drug discovery from a series of slow, disjointed experiments into a continuous automated learning loop.
And it's impressive to see the industry adoption numbers that are backing this all up. NVIDIA released their State of AI surveys this week, too.
They did. 91% of financial services companies are either assessing or already using AI. 90% of retail and CPG firms plan to increase their AI budgets in 2026.
The adoption curve is just vertical.
It is. But the biology sector, that's where the tangible change-the-world impact is really happening.
It definitely puts the PersonaPlex and the gaming updates into perspective. They aren't separate things. They're all components of the same machine.
They are. The voice agent lets the scientist talk to the lab. The simulation tools train the robots. The Blackwell and Vera Rubin architectures crunch the data. It's a full-stack approach to physical reality.
So if we step back and just look at this 1 week, January 11th to the 18th, what is the synthesis?
I think the synthesis is that NVIDIA is no longer just a chip company or even just an AI company. They are becoming the infrastructure layer for science itself.
The operating system for discovery.
That's a good way to put it. The Vera Rubin architecture, the BioNeMo platform. They're trying to do for biology what CUD did for graphics. They're trying to standardize the language of discovery.
It raises a pretty fascinating question about the future role of the scientist.
It does. I mean, if we have agents that can safely use operating systems and robots that can slash manufacturing costs by 70% and instruments that can think, how long until the role of the human scientist shifts entirely?
Shifts from what to what?
From being the person holding the pipette to being the architect designing the system.
Yeah.
If the lab is just this orchestrated fleet of AI agents and robots, the human becomes the conductor, not the individual player.
A conductor of an orchestra that runs 24/7, never sleeps, and learns exponentially.
Exactly.
That is a future worth watching. We'll be here to track it. This was The Deep Dive.